Hello everyone. This video outlines the paper Reducing Network Agnostophobia. Myself, Akshay Dhamija. This work has been performed at the Vision and Security Technology Lab at University of Colorado Springs under the guidance of Dr. Manuel Gunther and Dr. Terence E. Bolt. Agnostophobia means the fear of unknown. This paper is focused towards the response of deep networks to unknown or out of distribution samples. Deep networks have widely been applied to classification problems. Let's see an example using the MNIST digits dataset. The aim is to classify the 10 digits on the left. We use the LeanIt++ network architecture that allows us to produce a two-dimensional deep feature representation of the input images. Each dot signifies a unique sample, with the color signifying the digit it belongs to. In order to separate these feature representations, a deep network uses a fully connected layer represented by the 10 planes on the right. Now let's consider the response of such a network to non-MNIST or out-of-distribution samples. Here we use the CIFAR images and pass them through the network trained to only classify the MNIST digits. The CIFAR samples are represented as black dots. Another example with the Roman letters. From the previous responses, we make two important observations. First, the magnitude of the deep features of the known samples is far greater than the unknown samples. Second, the entropy of the known samples is far less than the unknown samples. Let's look at some history on tackling out-of-distribution samples. One of the first approaches was introduced in 1990 by Martin et al., where they discussed the application of a MNIST digit classification network to real-world problems. Their network modified the standard softmax by using an additional term to provide a fixed activation for the none of the above class. This activation results in a classification plane parallel to the feature plane such that center of the feature space has maximum activation for the none of the above class. The idea of an additional fixed activation subsequently evolved into the background class approach. Here, the training data for the network includes a small pool of non-MNIST or background samples, which in this case are the Roman letters. This enables the network to provide a different activation for the background class for every out-of-distribution sample. Rather than following the previous trends, we focus on exploiting the default behavior of the network. We aim at representing the out-of-distribution samples at the center of the feature space while pushing out the known samples to a minimum magnitude of psi. For this purpose, we introduce our two novel loss functions. The first loss, called Entropic Open-Set loss, aims at increasing the entropy gap between the known and the unknown samples. For known samples, the loss is the same as the cross-entropic loss. For the unknown samples, it aims at providing equal probability for all of the known classes. The second loss, called Objectosphere loss, aims at increasing the separation between the known and the unknown samples in the deep feature space. This loss is used in addition to the entropic open-set loss and aims at making all known samples have at least a magnitude of psi, while the unknown samples are reduced to 0. For evaluation, we propose a new metric called open-set recognition curve. The curve is produced after sorting all test samples according to the maximum probability assigned to any of the known classes. On the x-axis, it has the false positive rate resulting from the unknowns, and on the y-axis is the collect classification rate from the knowns. As seen in the figure, our approach outperforms the current approaches. Thanks for watching. For additional details, please refer to the paper.